Our third example is about air standard dual cycle. Now we have covered Otto cycle and diesel cycle, and we said that in the Otto cycle, we don't have, this is the PV diagram, we have compression and heat addition at constant volume. So we have this. So heat addition occurs constant volume. In diesel cycle, heat addition occurs at constant pressure. You see here. Three and four. In reality, in actual engines, heat addition occurs neither in constant volume nor constant pressure, but both. Actually, so if you really want to model, if you want to use a realistic model from 1 to 2, this is compression. And what we have is, we have some of the combustion takes place at constant volume and some of the combustion occurs at constant pressure. So actually we have 3, 4 and 5. Okay, so his heat addition occurs here and here, and heat rejection occurs here. So this is Q in, and this is Q out. So this is a better way to model internal combustion engines by using heat addition at 2 stages. Stage 1, constant volume. Stage 2, constant pressure. So if you want to really approach the Otto cycle, then you emphasize on heat addition at constant volume. And if you want to model diesel cycle, you emphasize heat addition at constant pressure. So dual cycle, so this is a dual cycle. Dual cycle can be used to model both Otto cycle and diesel cycle. So here you see that step 1 to 2 isentropic compression, 2 to 3 constant volume heat addition to the air from an external source, and 3 to 4 constant pressure heat addition to the air again from the external source, 4 to 5 isentropic expansion, and 5 to 1 constant volume heat transfer from the air. So this is actually a much better model which can be used for both diesel engines and also spark ignition engines. Now if you look at our example, an air standard dual cycle has a compression ratio of 9, and at the beginning of compression we have P1. Let me bring it here. Come on. Okay, so we have a compression ratio of 9, and the beginning we have 100 kilopascal, T1 300 Kelvin, V1 is 14 liters, so this is a huge engine. Heat addition is 22.7 with 1/2 added at constant volume and 1/2 added at constant pressure, so it happens in 2 stages. So determine the temperature at the end of each heat addition process in Kelvin, net work, thermal efficiency and mean effective pressure. So we know the operating data, and if we look at the PV diagram again, so here this is our PV diagram. So we go from stage 1, compression, 2, and heat addition at constant volume, 3, and heat addition at constant pressure, 4, and we go back to 5. Okay, and this is heat rejection, Q out. So this is Q in, and this is also Q in. Therefore, compression ratio is 9. What we know P1 is equal to 100 kilopascal, T1 is equal to 300 Kelvin, V1 over V2 we know that is 9, and V1 is equal to 14 liter, okay, which is 0.014 meter cube. And we know that Q23 is equal to Q34, which is 22.7 kilojoule divided by 2, 11.35 kilojoules. So if you really want to say this is actually Q23, Q23, and this is Q34. Okay, so these are known, and of course we are going to use again table A22 to determine each state. So what do we know about state 1? We know that T1 is equal to 300 Kelvin, P1 is equal to 100 kilopascal, and if you look at the table we read, this is U1 and VR1 621.2. So this is a reduced specific volume, unitless. State 2, what do you know? Isentropic compression. VR2 is equal to VR1 multiplied by V2 over V1, which is equal to 621.2 over 9, which is 69,022. Okay, so this is one known related with the state. T2, we know, what do we know about T2? T2, again from table A22, once we know this, we can determine that from the tables. So this is 700 Kelvin, hence U2 0.49 kilojoule per kilogram. So we reached state 2. Now state 3, what we know for process 2 to 3, we know that Q23 is equal to M U3 minus U2, which means that U3 is equal to Q23 divided by M plus U2. Okay, so this is what we know related with this. How about mass? We need to calculate mass. Mass is equal to P1 V1 R T1 from the ideal gas equation of state. This is 100 kilopascal multiplied by 0.014 meter cube divided by specific gas constant 8.314, molecular weight 2897 kilojoule per kilogram Kelvin multiplied by 300 Kelvin. So this needs to be of course kilopascal and kilojoule. Therefore we don't need to make any conversion, but normally we need to convert this to pascal and this to joule, and our result 0.01626 kilograms, so 16 gram of air there. Therefore U3 is going to be Q23 11.35 divided by mass 0.01626 plus U2 514.49, which is going to be kilojoule per kilogram U3. And from this information, if you go to the table, our temperature 1507, I'm sorry, 7.7 Kelvin, and H3, we need H3 because it is a heat addition at constant pressure. H3 we will need that 164,531 kilojoule per kilogram. So this is also required, and we calculated that. For state 4, what was state 4? State 4 is here. Okay, so this is the state 4. And for state 4, we have constant pressure heat addition Q34 is equal to MH4 minus H3. Therefore H4, which is, we need one property here, because for ideal gas enthalpy depends only on temperature. Q34 divided by mass plus H3, which is 11.35. We already calculated mass. Mass doesn't change. 1626 plus 164531. So H4 is going to be equal to 43.34 kilojoule per kilogram. Therefore, T4 automatically determined from the table, Kelvin, and we will need VR4 for the fifth state, 639. Okay, so how about state 5? State 5, what we know, VR5 is equal to VR4, V5 over V4, which is VR4, V1 over V4. And this is gonna be equal to VR4, V1 over V2, V3. Is this a trick? Why that's the case? Because P3 is equal to P4 and T3 over T4 is equal to V3 over V4. That's the reason why we can write it in this form. And if we put the numbers, VR5 is going to be 2.4639, 9. This is the compression ratio, 2007 2.9, and that's going to be equal to VR5 16.1298. So if you go to table A22, what you can read from there is T5 1158.5 Kelvin, and you can read also U5, which is 896.6 kilojoule per kilogram. So everything is known now, the temperatures, etc. So V cycle is equal to Q cycle, and that's going to be equal to Q23 plus Q34 minus Q51. So that's going to be equal to 22.7 minus, so this, the sum is 22.7. Q51 is equal to MU5 minus U1. So we already know that, and the result is going to be 11.60 kilojoule. Mass is known, U5 and U1 are already determined above. Then we cycle per unit mass is going to be equal to 701.4 kilojoule per kilogram when we divide it into per unit mass, where mass is equal to, in terms of, we had it in terms of gram, so 0.01626. The result is that. How about efficiency? The efficiency is we cycle per or divided by heat in, and this 11.60, 22.7. So this is an expected value of approximately 51.1%. This is efficiency, and mean effective pressure is V cycle divided by V1 minus V2, but V1 minus V, this is the compression ratio. It's better to write it in this way. And cycle 11.60 kilojoule divided by 0.014, 1 minus 1 over 9. So this is a meter cube. This is kilojoule. Kilojoule, again, kilojoule per meter cube is gonna be equal to, you don't need to make any more conversion, then the result is 932.1 kilopascal. So this is the mean effective pressure.